Atopic dermatitis begins as a biophysical failure of the epidermal barrier. Long before an immune response triggers a visible rash, the skin's architecture cracks, allowing a faint blue vapor of critical moisture to continuously escape. This failure happens specifically at the stratum corneum, the outermost protective layer of the skin. The exact rate at which this insensible water vapor diffuses through the stratum corneum is a measurable metric known as Transepidermal Water Loss, or TEWL. Accurately capturing this invisible vapor flux is notoriously difficult. Clinical metrology struggles to isolate the skin's natural evaporation from environmental noise like ambient humidity and airflow. The Wearable Analytical Skin Probe, or WASP, is a bioengineering solution designed to cut through that noise. It isolates the local microclimate to quantify this exact biophysical leak. While diagnostic tools like the WASP measure the exact volume of the deficit, targeted lipid formulations are required to physically patch the gaps. Treating atopic dermatitis requires viewing it as an engineering leak. The structural failure must be precisely measured before it can be effectively patched. A healthy stratum corneum relies on a tight matrix of specific proteins to aggregate keratin and maintain its dense cellular architecture. The most critical protein responsible for binding this barrier together is filaggrin. In healthy skin, filaggrin degrades into natural moisturizing factor. It breaks down into smaller, highly hygroscopic amino acids that spread hydration and maintain the layer's moisture. Up to 60% of patients with atopic dermatitis possess a genetic mutation in the filaggrin gene. This genetic defect causes a severe and immediate reduction of natural moisturizing factor within the skin. Without that moisture, the stratum corneum's pH level undergoes a direct pathological rise, shifting from its protective acidic state to a highly alkaline environment. This elevated pH mistakenly activates multiple serine proteases within the epidermis. These hyperactive proteases attack the surrounding tissue, physically snapping apart corneodesmosomes and tight junctions. The barrier's integrity is systematically dismantled. At the same time, this destructive enzyme activity actively downregulates the secretion of protective lipids from underlying cells. This biochemical cascade strips the barrier of structural ceramides, driving massive, unregulated transepidermal water loss well before the patient experiences any surface-level inflammation. Capturing the rate of that invisible vapor flux dynamically remains an ongoing challenge in clinical metrology. Standard open-chamber measurement devices are constantly corrupted. The readings fluctuate wildly based on ambient temperature, room humidity, and local airflow. Traditional closed-chamber devices seal out the room air, but they fail because evaporated water continuously accumulates inside the cup, quickly throwing off the measurement. This schematic shows the WASP wearable architecture. It uses a closed chamber flush against the skin, but integrates specialized fluidic channels. The core innovation is a cyclical pump system, driving a 60-second dry air purge, pushing accumulated moisture out through an exhaust port. This active purge cleanly strips out ambient humidity and vaporizes any residual standing water resting on the skin surface. The internal environment is forcibly reset, dropping rapidly to a baseline of nearly 0% relative humidity. The device then halts the purge, capturing a pristine 60-second sensor reading in a perfectly isolated, stable microclimate. An onboard desiccant filter allows the WASP to circulate this dry air internally. There are no external tanks, making the unit entirely wearable and untethered. By artificially forcing a zero humidity baseline, the WASP guarantees an identical, mathematically perfect initial condition for every single diagnostic reading. To process these clean sensor readings, the WASP relies on Fick's second law of diffusion as its mathematical engine. Fick's law allows the processor to calculate the exact water vapor concentration right at the skin surface, relying entirely on data gathered from the humidity sensor located at the chamber's ceiling. However, the capacitive relative humidity sensor suffers from a finite response delay. The hardware cannot react to moisture changes instantaneously. Higher moisture levels exacerbate this nonlinear lag, meaning the raw sensor data will naturally underestimate the true evaporation rate. Engineers bypassed this hardware flaw using standard wet cup evaporation tests. By measuring a known mass of evaporating water, they calibrated an algorithmic correction factor. This graph shows that custom algorithm. The correction factor scales linearly with absolute humidity, sloped to correct the delayed hardware signal. This correction holds perfectly up to 1.2 grams per cubic meter per second, hitting a hard ceiling representing the physical saturation limit. By bridging hardware lag with mathematical calibration, the WASP pipeline successfully extracts the true, undistorted water vapor flux. The combination of the dry air purge and fix algorithm allows the WASP to run continuously on human subjects. During clinical testing, subjects rest in a controlled environment to establish thermal equilibrium between the device and the skin before measurements begin. This chart tracks the output, plotting 10 continuous measurement cycles across various anatomical locations, including the forearm and palm. This continuous data stream easily distinguishes sudden spikes of sensible thermal sweating from the low, flat valleys that represent the insensible TEWL baseline. Isolating this steady, insensible baseline reveals the exact structural integrity of the barrier. An abnormally high insensible baseline points directly to the severity of atopic xerosis, identifying subclinical dry skin where the cellular architecture is already failing. Continuous dynamic mapping gives clinicians the data needed to pinpoint microscopic barrier dysfunction long before it triggers a systemic immune response. Once anomalous water loss is detected, pharmacological intervention shifts from reactive immunosuppression to proactive structural repair. Traditional inert occlusives like petrolatum merely sit on the surface of the skin. Rebuilding the barrier requires advanced physiological formulations. True repair introduces the precise structural components that were lost, specific ratios of ceramides, cholesterol, and free fatty acids. Ceramide lipids physically permeate the barrier, slotting directly into the gaps of the broken lamellar bilayer to seal the leak. Humectants work synergistically with these lipids, actively drawing sustaining moisture up from the deeper dermis and locking it into the newly repaired barrier. The formulation is completed by adding active anti-inflammatories, like licocalcone, to chemically suppress the localized cytokine cascade. This multi-pronged formulation patches the physical defect and suppresses the inflammatory trigger entirely from the outside in. Viewing atopic dermatitis as a biomechanical failure means it can be continuously monitored by advanced sensor engineering and structurally cured through precise lipid pharmacology.